Welcome back, everyone. I hope you are enjoying the conference so far. As we move into our next session explores blind wireless seed key exchange, heavy vehicle trailers using PLC4 trucks and KWP 2000 diagnostics face vulnerabilities in seed key authentication, enabling non-contact attacks that bypass ECU security. And this talk presents a practical analysis and experimental validation of these risks, highlighting the need for stronger protection of connected trailer systems. Joining us is Anne Jacos, cybersecurity research engineer at NMFTA, specializing in embedded systems and advancing cybersecurity in the trucking industry. Please welcome Anne Jacos to the stage. A quick note, please use Q&A section for your questions. And stage to you, please.
All right, thank you for the introduction. Um, like I said, I'm Ann Zakos. I'm a cybersecurity researcher over at NMFTA, the National Motor Freight Traffic Association, and we're going to be talking about blind wireless seed key exchange today. This presentation basically covers some research that was published onto a vulnerability that was discovered in trailer equipment, as well as detailing a timing-based reset attack that exploits predictability in seed generation. A quick agenda overview. I am going to start off with some introduction with the tools and technologies that were used for this attack, moving on to how we actually discovered the vulnerability on this particular piece of equipment, how it was done, how did we set up the hardware and all that, and then wrapping up with some conclusions and mitigations. And before we actually jump in, I do want to kind of set up a visual for you all to see, to visualize what this looks like. I'll go in deeper about this actual setup later, but so you have a picture in your mind of what it looks like going forward. And so starting very basic, I want to give some background into trailers and trailer architecture, because this was a vulnerability that was found in a piece of trailer equipment. And so trailers are not just bare bones. They did used to be a piece, they used to be more, they had brake lights, they had turn signals, and that was kind of it. And like any piece of technology, they've evolved through the years so that they're more involved. They have a lot of different pieces of technologies. They have a lot of different sensors. They have a lot of different protocols stacked upon each other, running on them. They're not bare bones. So this is kind of the stage where our the vulnerability that we discovered is set upon. And one of the pieces of technology that's running on these trailers is J2497, aka PLC for trucks. Now, this is a standard that has been around for a while. It was initially introduced to satisfy US regulation that required trailer ABS faults to be displayed onto the dashboard. Now, the lifetime of trailers is very long. The original purchasers may buy these trailers, have them in their fleet for decades, and then sell them again to someone else. And then those people will use the trailers for, decades more. So the lifetime of these pieces of equipment is very long. And then also the cost of retrofitting them is very high. So industry took it upon themselves to design a technology that would not require another connector. They could just use the existing technology that was already on the trailers, and in order to get the data out of the trailer and into the tractor. This is still the only industry standard way to do so, and as such, all equipment in North America specifically uses it. How it works is it basically encodes J1708 data into spread spectrum chirps. It works like any PLC power line communication network. And then another thing to note is ECU diagnostics on J2497 are always found in proprietary data link escape messages. You can see the photo on the screen. That just is a very basic LAMP on message in SIGROC. So the research that we did for this vulnerability specifically was not the first time that there's been research done into wireless vulnerability specifically for J2497. There was one done, there was a CVE released in 2020 where it was discovered you can read messages off of J2497 using active antennas from about 15 feet away. And then there was another one in 2022 where it was discovered you can actually write onto it using a power amplifier and antenna. And these all kind of build up. Obviously, it's hard to uh, you know, uh, read if you can't write. And so, like, all these vulnerabilities kind of build upon each other, leading into the vulnerability I will be discussing today. Now, another important piece of technology, or another important thing to talk about, is seed key exchange. It's right in the name of the presentation, so you can kind of tell it's important to this research. But what it is basically it's an authentication protocol that uses challenge response mechanics and is in place to prevent unauthorized access to privileged diagnostic and engineering functions. And it's basically just a handshake protocol. The diagnostic software starts off by asking the ECU, it says, hey, I want to do this privileged session or do this privileged function. The ECU responds, okay, I don't think you're authorized right now. So I'm going to issue the seed. The diagnostic software takes that seed, does some sort of transformation, computes some sort of function, and spits out a key, hence seed key. And then it responds to the ECU and says, this is the key I calculated. Does it, the ECU calculates the same key or using the same seed and says, okay, yes, this equals what I got. You are authorized, go ahead and do whatever you wanted to do. The most common diagnostic protocol is UDS, but it is not so the most common diagnostic protocol that uses seed key exchange is UDS, but it's not the only protocol that does so. There's also something called KWP 2000, Keyword Protocol 2000, which is important. I'll mention again in a minute, so keep that in mind. And then some other things to note about seed key exchange is there are different security levels that have different functions to do different things. And then typically seeds in modern ECUs are several dozen bytes long. So how did we actually, begin this research and decide that we were going to look at this particular piece of trailer equipment and do this testing and ultimately result in the vulnerability that we discovered? Well, it was kind of more happenstance. It was just something we kind of stumbled upon. We have NMFTA has an annual cybersecurity conference, and one of the years we were going to do a demonstration for everyone to show that one of the previous vulnerabilities that we were able to write the traffic onto the J2497. And how we were going to do this was by sending a chuff test, which is basically a puff of air which is released when you send a command to the ABS modulator to prove that they're working. And this is just a good way, an easy way to prove that you're actually writing data onto J2497, and because it's very audible. And as we were doing this preparation for this demonstration, we were going through the diagnostic logs, and there was a few things that we noticed that were a little bit different, that were kind of unusual. And the first was that there was actually authentication that was required to send this chuff test. Now, this was unusual because we've done this test hundreds of times on a lot of different pieces of equipment. And in all previous cases, there was all the previous targets just accepted commands without authorization. So the fact that this one rejected it and said, I need authorization for it was actually a positive thing. That's a step in the right direction, right? Because you want there to be authorization for sensitive actions, right? There is also something else that was a little bit weird. There were some services in use, and it was using a different diagnostic session level that is pretty not, it was unusual for UDS. And uh, all these things pointed to we were actually looking at KWP 2000, not UDS. And so from seeing these unusual things, we decided we're security researchers. So we're like, okay, we want to understand how this is working and how the authentication mechanism is actually occurring. So that spawned our research. Now, there are several ways to bypass seed key exchange. I'm not going to go through all of the ones that you see here on this attack tree, but this is a very good, I really like this graphic. I took it from a training that's used at Cybertruck Challenge. They have free resources online if you'd like to look up more. It's all available on the internet. But we decided that we wanted to do a time-based attack to see if we could just make the seeds more predictable through resetting the ECU. And, this is a fairly common initial vector to test to see if you can get it to work. We also did decide that we wanted to do it as a blind attack, as in we would only be transmitting to the ECU. We wouldn't actually be receiving any messages. We decided to go this route because it's a good benchmark to see what's possible, since it's the least complex and cheapest attack. So we went that direction. And the first test was super simple. It was just like a script of like 3 or 4 lines where we had it request, or we had the ECU be reset and then ask for a seed. So it just looped that a few hundred times or so. And as a result, we got a population of about 4 common seeds, making up a small portion of the responses. This suggested that yes, it was time based, but there was still some randomness. So as we were going through, and we had to figure out how to remove this randomness, reduce the jitter, and we made an assumption that some of this randomness is probably introduced due to delays in the software stack. So we had to calibrate the timing, make it more precise, and but the precise timing is not compatible with standard J2497 tools or RP1210 interfaces. So we had to use something else. Conveniently, in the previous research done for J2497, some SDR tools had already been written. So we could just repurpose those and tweak them so that they worked for the precise timing that we needed here. And that tool was called J2497-Keyhole. So when we were going through and we're calibrating this precise timing, the way we did it was we treated it like a glitch campaign. We set up a custom SIGROC decoder stack, and it displayed, you can see on the screenshot there, it's just a very bold pass fail, like did it go through or did it not? So we went through, we did that, we did a sweep of parameters, and we tried to decide what was the earliest time a request for a seed could be sent through after an ECU reset. This shows the different the screenshot of the different possible time slots that we got. So a few things to note. D was the place, I I can pull up my laser pointer up here so you can see. But so there was these 4 different time spots. Time D was where we got our reset request. So when we sent the ECU reset command, this is where we got the confirmation that it was received. Point A was actually the first time it was about 204 milliseconds. We found that a RX command was received. However, the issue there was it was only one message would actually, it was a one message queue. So if we sent something else, it would override it. So we ended up not actually using that time slot. The other two was there was time slot B, where was this is a there was a setup storm that occurred there. Um, we didn't end up going with that because there was potential issues. We were worried about adding jitter, and there was no actual collision detection occurring. So to be certain, we went with time C. This was the very first time where we got the seed request and it went through and it was all good. Now, there's both pros and cons to this. The obvious issue is it's a very long time slot. Like the difference between D and C is it's 6.5 seconds. That means the loops that we were sending for the testing were very long. The positive thing though was it was very deterministic. So the time delta between spot D where the reset request was confirmed and time C was very deterministic, and that was good, so we could just calibrate that in our timing. Now after that there was one last source of jitter, and that was the difference between when the reset command was sent at time 0 and when it was actually confirmed. And we wanted to reduce that jitter. So how we did that was we actually took advantage of a feature of J2497 addressing. It's not in the standard itself, it's just the way that it typically works, is it has dynamic addressing. So if an ECU is listening on the bus and it sees a message that is broadcasting from its same address, it will actually have this behavior where it shuts up and moves over. So, but we were doing a blind attack. So how do we actually take advantage of this if we don't know where the ECU is moving over to? Well, we fixed that by just broadcasting from every address except for the one specifically that we wanted to have the ECU move over to. And with that, we were able to groom the timing to be exactly as we wanted. And boom, this was our first win shot where we were able to get very deterministic seeds from after our reset attack. You can see we have 85A9, and that repeated several more times. This was our first attempt where we were able to get the results we wanted. So we were able to actually calibrate it a little bit more and get it a little bit more deterministic. But this was really exciting because it confirmed our hypothesis. And when we repeated the test, every time the first seed the ECU sent was 85A9. So a little bit about the setup. We used existing technology and adapted it to do this type of work. So we used a PLC test con. We broke out the signals into what we needed. We pulled them out. We connected them to a logic analyzer and then hooked that up to the laptop. And the laptop was running this whole stack. As you can see, I talked about it already, but we had the custom SIGROC. We were running SIGROC and it had that custom decoder set up on it. And it was very easy to visually tell whether what was going through was what we wanted or not. Again, going back to the actual hardware setup here, it's the same setup as was used in previous testing with J2497. This is not a new setup. But what it is basically there's an antenna. Let me go back. You can see in this picture a little bit better, but there's an antenna running along the trailer on these cones. They're attached to a power amplifier, a variable attenuator, and a FL2K, which is then plugged into a laptop. In addition to the wireless setup, we also typically had it where we modified a J560 cable and connected it to the trailer, so we would be able to tell when there was any hardware or wireless, there was any failures there. So we did all that. We were able to get a repeated key. How does that help us with getting the key? I mean, repeated seed, and then how does that help us with getting the key? Well, I would go back to the attack tree that was in a previous slide. There's many ways to do that. There's many ways to break seed key exchange. That's not anything new. So what we did here is we did the most basic, and we took traffic captures and logged the responses to the seed key exchange. So it was the known seed key and pairs, and we plotted that onto a graph. After that, the most simple test is to see if the seed key exchange transformation is either XOR or linear. That's the first test you do because that's the easiest, and you don't have to go any further with trying to break the seed key if you've determined that it's linear and XOR based. So we did that. We did a transformation, and it ended up being this was a pretty trivial uh, uh, to calculate the key for this particular ECU is pretty trivial. So it was actually just linear. So we were able to get the key from that, and there we go. We just needed to know the one key, actually. We just need to know the key for 85A9 and transmit that if we were to use this attack. So what is the impacts of this actually? So the actual breaking it down to numbers, the actual determinism for this, if you were just to run it on a loop for 30 seconds per attempt, the chances that you would get the seed that you were expecting was over 50%. Now, if you were to do the precise calibration, to do the exact timing, and have it run and have 2.5 minutes per attempt, the predictability is actually 90%. There's also good news in terms of this attack doesn't scale to arbitrary units. We tested about 4 different ECUs from different build dates, different firmware versions, and they ended up having different first seeds on each of these different ECUs. This is a good thing. However, this is just this means across different ECUs it doesn't scale. If you were to repeat this test and have it, run the SAM campaign and be able to find the first ECU, the first seed, it would still work for this attack would still work for that particular ECU. And then there's also the thing where more testing would need to be done to actually answer, like, how varied are these first seeds? Are they actually 1 out of 65,000, or is it less than that? So more testing would be needed to be done in order to answer that question. So here we go. This is the actual vulnerability that resulted from this research. It was published in 2024, and it has all this. It's the reset attack for timing based, for seed key exchange. And some conclusions that we came out of this research is that seed from diagnostic software is not actually sufficient to access the bootloader and engineering functions. We found that those did require different diagnostic levels from what we were finding from doing this attack. So that's a good thing that those are actually protected further from what we did. It also does not scale to arbitrary units, but it's not attacker useless. If you are looking to attack a particular make and model of an ECU, you would still be able to run that attack and make the seed be predictable. ECUs, which are susceptible to a reset attack due to timing-based seeds, are also susceptible to blind seed key unlock. That means that there are ECUs out there that have been previously assessed to be protected and not susceptible, but they might actually be. And then finally, mitigations against wireless injection onto J2497 are needed on all tractors, on all new tractors to protect legacy trailer equipment. We do have some mitigations and recommendations that have come out of this. We recommend that brake ECUs should be using cryptographically secure seed key exchange, as in Service 29 is a great option. We also have a comprehensive list of security requirements that NMFTA has published, and we recommend that trailer telematics should satisfy these. And finally, new tractors should protect trailers from wireless injection attacks. We have a full list of PDF of actual mitigations published out there where we detail some of these different protections. Finally, I want to just thank everyone who made this research possible. My colleague Ben Gardner, he has done a lot with this and with this research, so many thanks to him. We also want to thank all of the carriers and all of the fellow researchers who have supported and helped with this effort. This would not be possible without their help. I will conclude there and we can move on to if anyone has any questions.
Thank you. And have a couple of questions. Let me put it into the Q&A section and I can take it on stage.
Sounds good.
Okay, let me bring on this one. So, do you think electrical distribution box and fuses have a role to play in power line attacks? And any seed key or ECU tolerant mechanisms can be incorporated in the distribution box because encrypting power line is not easy and tricky, not just tiny. I think the question was not.
Yeah. So we're actually, this is one of the questions that still remain for this J2497 PLC research. We're actually not sure how it's wirelessly received by the trailer. We're not sure how, by transmitting these signals, how it's actually received and gets across there. So there's still some questions there. And yeah, we have some recommendations with, for example, the next generation tractor trailer interface, adding in protections there. And yeah, I agree. It's a it's a hard thing to protect against, and power line communication is pretty legacy piece of equipment, but yeah.
Thank you. And shall I
Hopefully
move
that
to the
answers.
next question?
Yeah, please. Yeah.
Given that a diagnostic vulnerability, blind seed key, can bypass a safety mechanism reset attack, how do we reassess our legacy ECUs to prevent a cyber incident from becoming a safety event?
Good question. So we have a list of, I'm going to reference um, the recommendations and mitigations that we have published. Um, but there are several things that um, there's something called adding in keyhole, uh, adding in keyhole, which is basically so that there is no, like, only messages can be received in this set amount of time, and then everything outside of that, the messages are ignored. So that's a recommendation for how to protect against these kinds of attacks on PLC. Um,
Thank
yeah.
you. Shall I move to the
Mhm.
next?
Go
I'm
ahead.
not sure how relevant it will be. You mentioned about like regulations which oblige the need of SBOM. Are there any expected maturity levels requirements for SBOM exist in these regulations? Um,
Um, yeah.
right?
I yeah. The I didn't mention S bombs, but
Maybe let's rephrase it in this way. Like, does SBOM can help to prevent key relevant security issues or the vulnerabilities which do appear?
mm, well, I think S bombs are a good uh just a good practice to do in general.
Mm.
And if you are able to, um, you know your population of equipment and um, having more detail into that is always helpful. So,
From the defense in that perspective, it helps to address the issue. Okay.
correct.
Uh,
Yeah.
we have another question. Let me bring it up. Do you think an add-on device could enable remote vulnerability? What is the line between cybersecurity and criminal sabotage?
Yeah. This is something that add on devices are always could always be a security risk. Um, there's been research done into, like, specifically telematics devices and plugging those in, and the risk of that those may introduce. So definitely, theoretically is possible, and there is research out there that has shown that it's theoretically possible. But we have not seen any of those types of attack out in the wild. Um, I'm thinking specifically related to telematics um, and third party telematics. The line between cybersecurity and criminal sabotage, well, um, I think that's depends on, you have to have good practices, you have to do good hygiene, like, it's the same, treat your assets like you would treat your enterprise environment, and, um, have, audits, and have, um, good practices and good processes in place, so,
The
yeah.
same thing can be used for good purposes and the bad purposes. It depends how you use it, right? That's good.
Correct, yeah.
I think
Mhm.
we are done with the questions. Uh, with that, if anybody has any additional questions and will be available at the backstage in the lounge area, please feel free to reach out her, connect with her, and you can brainstorm on a lot more technical details of the aspects which are presented here. With that, I would like to thank you, and thank you so much for all the insights and so much of information we've been provided. Lot to process. It takes a lot of time because entire research has been presented in a 30 minutes. So brain is
Mhm.
not equipped that much to process it immediately. But it helps a lot to gain this much of knowledge in a single shot in a very small period of time, and that helps the audience as well to see from the different perspective what could be explored and what are the risks are there. So thank you so much, Annie, and thank you so much everyone who joined for this session. We really appreciate that, and please don't miss the next sessions which are available. Please join it and have a great time. Thank you.
Thank you, everyone.